Okay, so let's look at this problem. It says a roller coaster car with a mass of 1,200 kilograms starts at the top of a hill with an unknown height. In order for the car to descend and make it through a circular loop with a radius of 15 meters, what is the minimum height of the hill? Assume no friction. So first let's draw a diagram. We've got our hill, and we've got our loop, and we've got our cart, which we know is 1,200 kilograms. We also know that the radius of our loop is 15 meters. And let's see if this is the ground. The height at the top of the hill is what we're looking for. So really, this problem has two parts to it, right? First, there's the top of the hill. And here's what we know about the top of the hill. Our initial velocity is 0. We're looking for our height. We'll call it height 1. And then the second part is the top of the loop. And for the top of the loop, we don't know our velocity there, but we'll solve for it in a second. We do have our height. We'll call it height 2. And height is just twice the radius, right? So that's going to be 30 meters. Okay. So let's also draw a free body diagram of the top of the loop, because this is going to be the most important part, for the cart to get through. So that's our top of the loop. Here's the cart going upside down. Still 1,200 kilograms, that's our mass. And we've got the force of gravity going this way. And we know from Newton's second law, force is equal to mass times acceleration, right? If it's force of gravity, that's equal to weight, which is mass times gravity. And then for centripetal acceleration, we'll rewrite it as mass times velocity squared. That's a 2 squared over our radius, since this is a loop, right, that we're going through. And then if we arrange all of that to solve for our velocity, or V2, then it's V2 is equal to the square root of gravity times radius. And then that, once you calculate it, right, should be 12.1, and that's in meters per second. Okay, so there's our velocity. Now let's talk about it in terms of energy. So energy at our second part at the top of the loop, we'll call it E2, is equal to our kinetic energy plus our potential energy. We can rewrite this as for kinetic energy, it's 1/2 times mass times velocity squared. And for our potential energy, that's mass times gravity times height, which at the top of the loop we do know. So once we plug everything in, we've got our mass, which is 1,200 kilograms. We've got our velocity at 0.2, I should say, which is 12.1. We've got our gravity, which is always going to be 9.8. And our height at the top of the loop is 30. So we can plug all those numbers in. And for kinetic, I have 88,200 joules plus potential 352,800 joules. Add that all together. Energy at the top of the loop is 441,000 joules. Okay, so there's our energy at the top of the loop, but not only that, due to conservation of energy, energy at the top of the loop should be the exact same as when the car is at the top of the hill, right? The only thing is initial velocity is 0. There's no kinetic energy happening, but we do know that there's potential energy. So again, energy at the top of the hill is equal to energy at the top of the loop. Energy at the top of the hill is just potential energy written as mass times gravity times height. We have our energy, right, which is 441,000 joules. We just solved for that. We're going to plug everything in. Actually, I'm going to rewrite this. So it's energy over mass times gravity should give us our initial height. And so at this point, we just plug in our numbers. Energy at the top of the hill, same as energy at the top of the loop, over mass, which is 1200, times gravity, which we always know as 9.8. And that should give us our height at the top of the hill. If you plug all these numbers in, you should get that the height at the top of the hill is 37.5 meters. So this is how high the hill needs to be in order for it to descend, make it all the way through that 15 meter radius loop, and go on. All right, and there's our answer.